Hello friends, and welcome to the last video of chapter number 6, that it is titled Adaptive Filters. We have learned so many concepts for the design of the adaptive type of the filters, either finite impulse response type or the infinite impulse response type here. The most popular topic from this particular chapter is the LMS algorithm, and here we are going to have a practice of the last problem. This is the sixth problem. So this is actually based on the application of LMS algorithm, standing for the least mean square algorithm here. So actually, for design of the finite impulse response filters, we have the knowledge of steepest descent algorithm, and then the LMS algorithm, that is having overcome over the limitation of the steepest descent algorithm. The previous problems we have solved based on to the understanding of the steepest descent algorithm, and then the LMS algorithm for various aspects as like the convergence, and then further the design of the LMS algorithm that we have done in the previous problem here. Now let us have the last problem, where we are provided the adaptive filter structure, and we have to write down the LMS algorithm for updating the weight, and also we have to determine few of the aspects associated to the LMS algorithm. So let us see what is the exact problem statement and how do we solve it to find the answers. So let us begin with the topic. So here we start with our topic, that is problem 6, adaptive filters. Here we are provided the problem statement. The problem statement starts as, consider the single weight adaptive filter shown in the figure below. See, we have part A, part B and part C to be solved. After this figure, we have part A, where we are asked to write down the LMS algorithm to update the weight denoted by W. In the part B, it is, suppose that x of n is a constant. X of n is denoted as opting the value capital K for n greater than or equal to 0. Otherwise, x of n will opt the value 0. So this is the definition of x of n to be a constant. We have to find the system function relating the d of n to e of n using the LMS algorithm, that is find capital H of z in the figure below. And part C, the last part of the problem statement, that is to determine the range of the values for mu for which H of z is stable. Getting back to the start of the problem statement, here we have been provided the single weight adaptive filter. So this is the schematic. You see on the left hand side we have the two input signals here. Either you call signals or these are the discrete time random sequences here. See, x of n is the signal here. That is the practical signal that is having the desired information as well as the noise or the interference component here. Whereas d of n is the desired signal to be available successfully decoded at the receiver end here. So these are the two input operands I can see here. For the adaptive filter structure, we have the use of weights. Here the W denotes the weights here. Now we have the summation block here, where d of n is added and x of n fed as input to the filter through the coefficients denoted by weight coefficients denoted by W is subtracted here, and finally we obtain the error signal here. Now coming back to the part A to be solved here. In the part A, we have to write down the LMS algorithm to update the weight W, and this is the part B, and finally the part C here. So now see, for the LMS weight update equation, we have W suffix n plus 1 is equal to W suffix n added by mu into E of n into x of n. So W suffix n is the weight vector, whereas W suffix n plus 1 is one step advanced to it. Mu is the step size, E of n is the error signal, the difference of the desired signal and the relative signal here, and x of n is the input relative signal here. So the question that it was, write down the LMS algorithm to update the weight W. So for updating the weight with the steps here, we have this equation: W sub n plus 1 is equal to W sub n added by mu into the error signal E of n into the input signal X of n. So this is the straight answer to this particular part of the question. Now in part B, here you see in the part B, we have been asked to have consideration that the input discrete time random sequence to the adaptive filter is a constant. Mathematically, it is represented that x of n is equal to the constant capital K for n greater than or equal to 0. Otherwise, it is opting the value 0 here. Now, we have to find the system function relating d of n to e of n. D of n is the representation of desired signal, whereas E of n is the representation of error signal. We are already shown with the schematic here where you can find D of n and E of n, and this relation we have to show by using the LMS algorithm, that is to find the capital H of Z. So this is the system transfer function in between the relation from D of n to E of n here. So the schematic is also shown to us. On the left hand side we have D of n, and on the right hand side we have E of n here. So let us solve this. So with x of n equal to a constant here, the error E of n we can determine. See, E of n formulation is D of n minus the estimate of D of n. So D of n we keep as it is, and the estimate of D of n, as we know it to be a constant input discrete time sequence, so it will be K multiplied by the weight W suffix n here. So here W suffix n is equal to W suffix n minus 1 added by mu into capital K into E of n minus 1. This is according to the update equation of the LMS algorithm here. So therefore, when we perform the difference E of n minus E of n minus 1, so this is equal to D of n minus D of n minus 1 minus capital K, representation of the constant to be the input sequence, multiplied to W suffix n minus W suffix n minus 1. We can also express it to the form D of n minus D of n minus 1 minus mu into K square into E of n minus 1, the use of step size here. So for the system function where the input is D of n and the output is E of n, the relation we can express with the help of the system transfer function into the Z domain, that is equal to capital H of Z, the ratio of capital D of Z to that of capital E of Z. So this we express as 1 minus Z inverse divided by 1 minus, in the bracket, 1 minus mu times capital K square, the bracket is completed and further multiplied to Z inverse here. So this is the solution to part B of the problem statement, and then we have the last part, part C, to be answered. The part C question is determine the range of the values for mu, that is the step size, for which H of Z is stable. See, the filter, adaptive filter will be stable if we have the condition satisfied, that is mod of 1 minus mu into capital K square is less than 1. So to apply this particular condition, it implies that the mu step size will be in the range mu is greater than 0 but less than 2 divided by capital K square. So the range of the values of the step size for which the stability of H of Z is there, here it is the range from 0 to 2 divided by capital K square. So it should be greater than 0 but less than 2 divided by capital K square. So this was the problem statement based on to the popular LMS algorithm here that we have learned in the chapter adaptive filters, the 6th chapter here. So this was the last video. By the next lecture, we shall be starting a new chapter in our subject advanced digital signal processing, and the chapter it is wavelet transformation, and we are going to address the first topic from that particular chapter, that is the origins of wavelets. Thank you.